First order ordinary differential homogeneous functions. Today class, today we'll be looking at homogeneous functions under first order differential equations. We're looking at homogeneous functions under first order differential equation. When do we say a function is homogeneous? When do we say a function is homogeneous? Now let's look. A function is said to be homogeneous a function is said to be homogeneous if and only if a function is said to be homogeneous if and only if we introduce a factor known as what? Lambda. So the function of the lambda of the x, so the function of lambda of x and the lambda of y. And if after expressing it, we can get the lambda on its own raised to a certain power n times the function f of x, y. So now, this is what it means. If we want to know that a function is homogeneous, when we introduce a lambda in the function, that is function of a lambda x and lambda y. And after simplification, we can factorize our lambda raised to the power n times multiplying the function. And we can equate the two of them as the same thing. Then we say this function is what? An homogeneous function. We say this function is an homogeneous function. Now, the function will now begin to have a degree of n. So this function will have a degree of n, which is also known as the index of the parameter. The index of the parameter. And the parameter we are using here is lambda. And the parameter we are using here is what? The lambda parameter. Let's take two examples and look at and verify whether it is homogeneous. So now example 1. If you have a function of f of xy, which is equal to x exponent 4 minus x cubed y. Let's look at this function, whether we can verify that the function is homogeneous or not homogeneous. Alright. So now with this function, for instance, we now introduce our lambda of x and our lambda of y. And that would be equal to lambda x all exponent 4. So whenever you see x, you put lambda x. Whenever you see y, you put lambda y. Minus lambda of x exponent cube multiplying the lambda of what? Of y. So now when you express this, you get the lambda exponent 4, x exponent 4, minus your lambda lambda times lambda will give you lambda exponent 4, x exponent 3, y. Alright, so now time the lambda is exponent cube, x exponent cube times another one and this. So lots of indices because the bases are the same. Okay, so let me expand it for you. So you get something like this: lambda cube, x exponent cube, s cube, multiplying lambda what? Y. So now because this base and this base are the same, you get minus lambda 3 plus 1 that gives 4 s cube y. Alright, so now when you have something like this, what happens is that you can factorize, you have to factorize the lambda out and see whether I can multiply the function. So now if we factorize the lambda out, you have lambda raised to the power 4 multiplying x4 minus s cube y. So because you are having the function multiply the lambda of 4, which is multiply the function f of xy, then we can say this equation or this particular function f of xy is homogeneous. So this function is what? Homogeneous. It's an homogeneous what? Function. You can say then this function is what? An homogeneous function. And it has an index of what? 4. And this function has an index of what? 4, because the lambda is raised to the power what? 4. Alright, let's verify another one. We have f of xy, which is equal to e exponent x of y plus the tan inverse of y on x. E of f of y plus the tan inverse of what? Y on x. Let's see whether this equation is also a homogeneous function. So now, This is an homogeneous function of degree 4. Let's see whether this is also a homogeneous function. So now we introduce our f of what? Lambda x, lambda y, which is equal to our f of lambda x, e of lambda y divided by lambda y, plus our tan inverse of lambda y divided by lambda x. Alright, so now what happens here is that when we want to solve this particular equation, because of the state of the lambda over here, this, when you solve it, you get 1. You can divide the lambda over here, so you can get what? Back your xy, and when you do this too, you can also divide the lambda and lambda over there, so you get back your tan inverse of what? Y on what? On x. But what happens is that before you can take this lambda and lambda out, and you get back to your function, that means it is multiplied by lambda raised to the power 0. Because any number raised to the power 0 is 1. So lambda raised to the power 0 is 1, like 1 times this. Are you getting it? So therefore, this is a homogeneous function. It is a homogeneous function with a degree. A homogeneous function with a degree of 0. So it is a homogeneous function with a degree of what? Of 0, because you can take the lambda out of the equation and you get the function again, and you multiply it by lambda raised to the power 0. I get it. Alright. Now the last example, we have f of xy, which is equal to x squared plus sine x cos what? Y. F of xy, which is equal to x squared plus sine x cos y. So now if you want to really solve this, it becomes f of what? Your lambda x, your lambda y, which is then equal to what? Lambda x all squared plus sine lambda x cos lambda y. Now, there's no way you can try on your own, but we've tried it already for the sake of the video. There's no way you can factorize the lambda out. No. In this particular question, there's no way you can factorize the lambda out. You'll be getting different degrees for the equation. You'll be having a lambda of degree 2, you'll be having a lambda of what? Degree 1. Are you getting it? When you simplify everything, you'll be having a lambda of degree 1. So since you can, that is happening, yes, lambda of degree 2, yes, lambda of degree 1, you can't factorize the whole lambda out to multiply the function. So therefore, this is not a homogeneous function. This is not a homogeneous function. Alright. Thank you very much for joining. Let's look at the next video where we talk about reduction to separable form.